Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm very happy to introduce Ashish Kapoor, our first speaker for the day. Ashish is from our Redmond lab, like some of the other speakers you heard earlier in the week. Ashish did his undergrad from IIT Delhi and then went on to do a PhD at MIT, and then since then he's been working with us at our Redmond lab for many years. I leave Ashish to tell you more about what his interests and areas of work are. Over to you, Ashish. Thanks so much for coming here.
All right, thank you, Satish. So thank you everyone for coming. So just to give you a background, I did my undergrad at IIT Delhi. That was a long time ago, and at that time, no one was thinking about machine learning, at least IIT Delhi, at IIT Delhi then. And the first time I heard the phrase was really in the grad school. So my PhD ended up in machine learning, right? And since then, I worked in a lot of different areas, including human-computer interaction, computer vision, but recently grew, very interested in this whole arena of swarm sensing. So where you are thinking about all these devices that could sense different kind of phenomenon. And today we are going to speak. I'm going to tell you about a very specific kind of swarm sensing, which I think can be very useful in measuring some of these weather phenomenon, right? So that's the title of the talk, planetary scale swarm sensing, planning and control for weather prediction. And a lot of this has been joint work with many folks. So Eric Horwitz, who runs the Adaptive Systems and Interaction Group, Debadipta Day, who recently joined us from Carnegie Mellon Robotics Institute, Andre Kolobov, Rich Caruana, both of them looking into the machine learning side of things, H.A. Kamar, and we have Aditya Grover and Dravyansh, who were undergrad at that time from IIT Delhi and interned with me, and they contributed significantly to this work, and of course Amit Deshpande, who's been spearheading the theory part of some of this work, right? So let's get right into it, and feel free to interrupt. I mean, there is a lot of stuff that I'll be throwing at you. I mean, not just from machine learning, but also from linear algebra, from discrete optimization and things like those. So we can go as slow as you guys would prefer. So just feel free to interrupt me with questions. So the research question that we're asking in this work is that, can we build a swarm sensor network, right? So swarm sensing, what it is the idea that you have lots of, probably thousands of sensors, right, that might be autonomous. They can communicate in a seamless manner, either in a centralized manner or in a distributed manner. And the whole purpose of them is to sort of sense the environment, right? So the first question that we're going to think about is that, how can we build such a network that has the capacity to acquire relevant information so that we can build the predictive model part of it. So this is the machine learning aspect of our problem, right? How can you start thinking about architectures that can acquire relevant information? So it's information that's relevant to the task that you care about. And then of course the idea is to build a predictive model. So here is a machine learning plus. So it's not just about sensing. You also want to build the mechanisms so that these agents can reason about where to sense. So I'll give you a very simple example. Consider this room, right? And you want to build a very detailed temperature profile, right? You are an air conditioning company and you want to figure out what are parts of the room are cold, where they are warm, things like those. And I give you only 5 sensors, right? So you have only 5 sensors. Why? Because those are hardware devices, they're expensive to build, right? So where should you place them in this room, right? And that's an interesting combinatorial optimization problem. So that's the, just to give you a sense of what it is. Similarly, in our problem, right, when you're doing weather sensing, you have huge sky, right? You'll probably have 100 or 1,000 sensors. How do you decide where to deploy them? That's going to be a function of not only your budget, your capacity, but also the function of the environment. Where's the uncertainty? What kind of phenomenon that you are seeing at the current moment, right? So that's the second thing that we're going to talk about. And more importantly, this is also a control problem, right? Once you build your device, once you figure out where to deploy these sensors, you also have to carry this mission out safely, right? So that means, like, if you have a sensor, if it's a robotic platform, it will have to go to that location. So consequently, it's also a controls problem, controls and planning problem. You have to start thinking from that perspective as well. So, this lecture is going to hit on all of these three things one at a time, right? As I said, we can go as slowly as we want, or we can just look through it. Like, there's a lot of material in here. So let's start looking at the first question. So as I said, in our context, the whole goal is to build a sensor network that for the weather prediction, right? So to give you a brief primer on what entails weather forecasting, a lot of weather forecast models recently have been physics based. So the whole idea is that you have all these physical laws, gas laws, Charles laws, Boyle's law, the pressures, the temperatures, and how they interact with the environment. And a lot of these weather predictions models are based on such physical sensing. So physics is definitely a big part of it. Laws of thermodynamics, and of course statistics, right? For instance, that the average temperature in Bangalore during the month of July is 20 degrees Celsius at this hour, right? Very unlikely that you're going to see 45 degrees Celsius, right? So there is a lot of statistics that you can leverage as well, right? And of course, there's some time series analysis, and finally machine learning. You can look at the features such as the terrain, such as the patterns of winds, and things like those, and they can provide you some signal about the weather. But in the end, it's the combination of the physics, the statistics, and the predictive model that's going to give you the biggest boost, right? So here is a graphical model. How many of you guys are familiar with a diagram like this? So again, we don't have to get into the details, but what it is a way of describing dependencies, in random variables that you might be interested in. So without getting into the details of the slide, let me just give you a brief intuition. So weather consists of 4 different phenomena. I'm again making gross approximations, right? So if you knew temperature profile, the pressure profile, the wind profile, and relative humidity, you covered most of the aspects, right? So let's just walk through this slide, one at a time. So these are some of these the variables that are encoding these things. So we have temperature at a location J, pressure at a location J as well. This is the dew point, which is relative humidity, and these are the wind vector. When wind has a direction as well as magnitude, so it's 2-dimensional, right? So this is a 5-dimension quantity, right? So what this graphical model entails is a statistical dependence between these guys through a deep neural network. If you're familiar with deep neural networks, they can be used to model joint statistical dependencies. So that's what this thing is. It's basically saying that if I know all of these guys, this neural network basically imposes some kind of statistical dependency, right? Let me make this problem a little bit simpler. Instead of looking at all the 5 variables, let's just look at one variable, right? And we'll come back to the slide later on. So let's look at different ways that currently our weather models are being informed. So the first thing is the satellites. The satellites are probably one of the most relevant information. So these are satellite imageries, both visible spectrum as well as non-visible spectrums, right? Oops. The problem with satellites is that it's sparse in space and time. Satellite would only revolve once every few hours and will only be able to capture a very specific geographic piece of land, and the resolution is not that high, right? The second thing is ground stations. So you have all these airports and ground stations where they'll have these weather sensors, and you'll be able to detect temperature and some pressure profiles, things like that. Problem is, of course, they're on the ground. You want to ideally characterize weather all the way up till stratosphere if you can. But however, one of the very important sources of information are these weather balloons, right? So here is a weather balloon, right? What it is, it's a helium-filled balloon with a payload. So at least in US, there are around 250 or so locations across the continent that they'll release these weather balloons twice a day. So 6 a.m. in the morning, 6 p.m. in the evening. And what these weather balloon carries is a payload that will measure some of these phenomena that we're interested in, and rise through your atmosphere up till say 100,000 feet. It'll then burst. The payload will come down. It has a GPS beacon, so someone can go and pick it up, right? And you get the data. One of the the cost of this weather balloon is probably like around the order of $1,000 or so, right? 250 locations, twice a day, looking at a $500,000 a day operation, right? And that's for US, and it doesn't give you that much resolution. Look at the state of Washington. Redmond is where I come from. Huge state, 5 locations, right? Each of them few hundred miles apart, right? So this gives you very valuable information, right? So you need to have something like that. But what you really want to do is we want to sort of make this efficient. We want to, think about, so this is a sensor network, right? Except the fact that you don't have any control where it goes. It'll drift with winds, sparse in space and time, right? So let's just focus on winds. I talked about 4 different variables. Let's just, for simplicity, focus on winds and how we can sense them, right? Our goal is to replace these weather balloons, with, robotic aerial platforms. So people call them drones, but quadrotor is probably the more technical correct term, right? And the prior art, as I said, that NOAA, which is responsible for generating these weather forecasts, makes predictions at 176 different locations across US. And these predictions are generated by instrumented weather balloons, plus wind profiling radars, plus satellite imageries, and there are other kinds of things that people have done as well, right? So, here's a detailed map, right? Again, very, very sparse, both in space and time. So here is another sensor network, right? And this is a sensor network that no one has explicitly deployed. But what it is all the airplanes at a single given moment at continental United States. There are 10,000 of those, right? So it's a sensor network. Of course, it doesn't sense anything, right? But can we do something intelligent there, right? Eventually, we want to sort of, deploy quadrotors, but the problem is that in order to, before we do that, we need to do some feasibility analysis. We need to figure out whether this makes sense, right? And this is a way to sort of study that if a dense sensor network would give us anything better than what we already got, and if it does, then by how much, right? So each of these airplanes is being tracked, right? And so we have some information, but we don't have the temperature profile or the wind profile they're encountering or things like those, right? So the first question is, how can you actually look at phenomenon, something like that, and extract some relevant information, right? So any questions so far? Yeah, go ahead. Say that again.
You are telling that there are 4 or 5 parameters. One of them is the pressure.
Yeah.
The pressure of a particular location. Pressure change, like temperature changes every day.
So it's a time series actually. So what you're asking is that are you also looking at the change in pressure as opposed to the absolute pressure, right? Is that the question? So the way I have described it, it seems that it's a snapshot in time, but what you're actually looking at the time series evolution as well. So those features do get encoded when you're doing it. But you're right, I mean, the gradient of pressure is a very important quantity that will tell you about the forecast, right? There was another question? Yeah.
So these aircraft, are they landed on the airport?
No, these are in the air.
So if they are flying, so they may be flying at like 35,000 feet. So they're like, does they, that data is important because we need the total mass.
Yeah, so good question. So the question is, I mean, most of these airplanes are flying at 35,000 feet. What kind of information can they provide at the lower altitudes as well, right? That's the crux of the question. So if you look at the altitude profile of these aircrafts, they range from 20,000 feet all the way to 35,000 feet. And in fact, we do have some aircrafts which are flying as low as 6,000 feet as well, right? But you're right, a majority of the information that we're gathering is at high altitudes, right? But here's the beautiful thing, right? This is a physical phenomenon. There is a smoothness, right? The wind on top are probably the highest velocity, right? So jet streams and things like those, you're getting into that range. And they do affect winds all the way till the ground, right? So there is friction, and so you're rarely going to see a dramatic change, as you come down. It'll be a smooth change, right? Unless there's a pressure gradient, for instance. So there are these kinds of physical phenomena, physical laws that bootstrap all this information down. So if you can do really well, good sensing at the top, it will percolate down all the way, right? It's not a discontinuous phenomenon. It's a very natural, physical phenomenon, right? Yeah?
But has it been validated? For example, I mean, he's saying in lakes and rivers that it's water that is mixing up, but in lakes that are static, there is a nice top layer.
Yeah.
The sun is reaching, there is a little mixing layer, and there's a bottom layer.
Yeah, in fact, here as well, as the wind profile, as the temperature profile, there are phenomena such as inversions, right? But the whole point is that this is a physical phenomenon. There is continuity, right? And of course, things might take a reverse direction, right? But it's all coupled together with other variables. So the information will percolate down, right? And I mean, as we'll see some of these examples as I move forward, right? Okay. Yeah.
You said that earlier you take only twice a day, readings twice a day. Here you will typically be doing it all the time?
Exactly, yeah. I can update my wind model every minute.
So that's what you typically plan to do?
Yeah, I mean, we are already doing that. We'll see. Yeah. So basically, here, what you'll get is you'll get observations every time you ping this network, right? And you can keep updating your model at a fidelity that wasn't possible earlier before, right? So, pretty much every minute if you want to do that, if you have the horsepower. Yeah. So let's get into the details. So that's the next part of the talk, right? Because this thing is available. This is publicly available data. Why do I say it's publicly available? So imagine if I do flight status from Jaipur to Bangalore, right? It'll tell you, oh, 1 hour flight. Just put it on Bing or any search engine you have, right? It'll tell you the flight is here. Estimated time in 1 hour or so, right? Now imagine if I had statistics of that single flight for the entire past year. That on an average from this position it takes probably an hour with a standard deviation of plus minus say 15 minutes. But today it's going to take only 45 minutes. That's a signal that you have a tailwind in that direction, right? So that's the intuition, and I'm going to formalize this as we move forward. But the thing is, take that information, integrate across the entire fleet of airplane flying, and you have a very high fidelity wind model, right? So the whole idea is that you can use wind model extracted from this information as probably one of the most refined wind models that has been out there, and then you can sort of reason out how far NOAA and other forecasts are from this model, right? All right, so let's get into the basics. This intuitions that I talk about, like how do I mathematically write it, represent it. I'm assuming all of you guys are familiar with vector algebra. This is like high school vector algebra, right? So here is the, here is the direction the nose of the aircraft is pointed in, right? And one of the things about the airplanes is that, you are not jockeying your throttle. You set your throttle to a certain airspeed and it's always going at that. And that's the airspeed that, someone has to declare all the way, right? So it's basically you have some intention direction of the travel. So the nose is fixed in one direction. The wind acts upon it and it results in something else, right? So there is a red is the direction of the nose. The wind is acting from the top and green is the resulting direction, right? I can basically, do a wind triangle, which is, nothing but vector addition. The heading plus airspeed, wind velocity gives me the observed ground track and ground speed, right? Very simple, right? No magic about it. So the intuition is that if I knew two of the variables, I should be able to reason about the third, right? So if I know what's the observed track and the velocity and the heading and the airspeed, simple vector subtraction to get that. But the question is, can we do that, right? How do I map, the intuition that I told you to something like that, right? How many of you guys have looked into things like Flight Aware or Flight Radar? Is that a website that you've gone to, right? So yeah, basically it's a publicly available data set that anyone can query. They have APIs. You can write your small, Python or C# or whatever things that you're interested in, and you can just query. Tell me about this flight, right? You can write your iPhone apps. There are very interesting iPhone apps based on this data. So for instance, you can hold your iPhone app, point in a direction, right? From the accelerometer, it'll figure, and the GPS will figure out where you are, which direction you're looking into, and then query this database, and it'll tell you, all right, there's a plane going there from here to here. I mean, there are very, very interesting things that people have done, right? It's all publicly available data, so you can party on it if you'd like to. So one thing that you can do is that if you go on this website, just hover the mouse over, it'll give you this information, right? So this is the same information that all the search engines use to give you flight estimate time and things like those, right? And there are information there. So for instance, it'll tell you what altitude an airplane is flying, in this case 37,000 feet. What is the ground speed, which is the 500 knots right now, right? And what is the track? So the green vector, right? It also gives you the latitude, longitude, right? So we know the position where it is, right? And we have some information. So basically, what we got this green vector fully covered, right? We don't have the wind velocity, and that's what we're interested in, but we don't have this either, right? So it's an ill-defined problem. With the GPS, they can monitor the ground track, but they can't tell where the nose of the airplane is pointed at, like how it's doing the wind correction. Of course, onboard computers can compute it, but for some reason that data has not been broadcasted. Right? It's one of those classic cases where you have the information, but the designers didn't think it through. So, you end up with the case where you cannot reason about wind velocity very easily. So it's an ill-defined problem. So what do we do? So let's dig a little bit through. If you basically do a little bit of more work, it reveals something called a flight plan. Right? So in the flight plan, what it tells you is that what kind of aircraft it is. It kind of tells you the route that it's going to take. I mean, this is it's a route in terms of the FAA waypoints, but it also tells you something called airspeed. What is the airspeed? So what airspeed is the fact that in a stationary air mass, at a particular throttle setting, the airplane will always go at a particular velocity, right? And that's how, a boat, an airplane, that's how they fly, right? And if the air mass is moving with certain velocity, your ground speed is also going to change with that, right? So in that case, you see that they planned for 452 knots, which is still air, which is the airspeed, right? But they are going at a 505 knots, which means they have a little bit of a tailwind going in this direction, right? So again, coming back to our diagram, what we got is that we've got some idea of what the magnitude of this vector is. So it's not that we don't know anything. We know a little bit what the magnitude is. Of course, we don't know the direction. And interestingly, the regulations also state that if an aircraft is going to deviate from what they have filed for by plus minus 10%, they'll have to update the system. So you kind of know that you have a good ballpark idea of what this magnitude is, right? It's still an ill-defined problem, right? We still need one another variable to reason about it. So, we are going to use something called spatial smoothness. So before I get into it, any questions on this? Yeah, this is a 5-minute delayed, but yeah, near real time. Right? So pretty, yeah, go ahead. Say that again? Yeah, so this information is all coming from the aviation authority in US, which is FAA, right? What they do is they track pretty much every single airplane on the air using radars, using other forms of communication, and they broadcast it to everyone, right? And there's no direct communication with the airplane. Ideally, you'd like to partner with every single airline in the world and ask them to broadcast all the data to you, but commercially it's an infeasible, right? So this is basically, all this is, you're doing simple web queries, right? I'm not talking to any agency, right? I'm just writing my web APIs and just gathering all this information.
And so some information about degree on the earlier thing, that's
Yeah.
the green one or
So in here,
25 degrees track?
yeah, exactly. So this is, you're basically looking at the GPS track, the
That's not the angle we are looking at, the original trajectory degree.
Yeah, so the green vector is known.
That's
So that 125 degree is the green vector. We don't know the degree of this guy, the direction of the red vector. Because if we knew, then it will be a very simple problem to solve, right? So what do we do next, right? So here is another intuition, right? There is spatial smoothness, right? What do I mean by spatial smoothness? So consider one airplane, and that's the wind triangle corresponding to that particular airplane. So you can plop these wind triangles for every single airplane in the air, right? So every single airplane is, has the corresponding wind triangle. So one spatial smoothness assumption that we make is the following: if two aircraft, they are close in space, they will have same wind vector, right? So it's a pretty basic, assumption, right? And because of the physical nature of the wind, we know that this holds, right? And to give you another intuition, so imagine that instead of these airplanes being distributed all over the space, if they were at the same location, right? I could just use some kind of simple averaging in order to get the wind speed. But however, they are distributed apart, so I need some way of encoding spatial smoothness. Yeah.
How do you define the boundaries of spatial proximity?
Yeah. So we have a kernel function. Are you guys familiar with kernels like SVM, support vector machines, right? So there also you are encoding the notion of smoothness using kernels, right? So how many of you are familiar with support vector machines? Right. So okay, so few of you, right? So in support vector machines, you have this notion of a kernel, which is a dot product in some Hilbert space, right? And what's its encoding? It's encoding the notion of similarity in feature vectors, right? So that similarity is the same thing, right? So similarity here is similarity in space. If two airplanes are close in space, their winds that you're seeing should be correlated. They should be, highly similar, right? And in this case, as you'll see, we're using a radial basis function to encode it. But again, the goal of this lecture is to give you intuitions so that you can start at least thinking about how to, construct some of these models for real world phenomena. Because when you start deploying some of these swarm sensors, they are going to be very dependent upon the application, right? And it's important to sort of start to, to see the thought process that results in some of these, inferences, right? All right, so the last thing we needed was that nearby aircraft experience similar wind, and that's enough for us to actually do some kind of a statistical inference on the wind. So I'm going to describe to you the graphical model that we started, right? And the graphical model is a way of describing statistical dependencies, right? We'll go through this slide very slowly, you know, and it's one of the technical slides, so feel free to just, you know, bug me as we walk through this. How many of you are familiar with Gaussian processes? So half, I would say, right? So let's go through this, right? So W, what is this? This is a latent variable that encodes our wind field, right? So W is a giant matrix. Let's think about that. Each entry in the matrix corresponds to a latitude, longitude, and altitude, right? And the entry corresponding to that cell is the wind, you know, in the x direction, for instance, right? So that's what W is. Similarly, we have a WY as well in the y direction, right? But I'm just for sake of clarity writing that as a giant random matrix W, right? What we are going to do is we are going to induce a Gaussian process over this wind, right? And what does it mean? It means that I'm going to look at two cells in that matrix, right, and compute a similarity function using a radial basis kernel, right? So basically saying that two geographical locations, if they are nearby, you know, without knowing anything else about the world, this is my assumption. What I'm saying is that, you know, it's a Gaussian process with a zero mean and a kernel function k, right? So if ith and jth cell, the location corresponding to them is close enough, you know, they should have a very high correlation, right? That's the intuition behind it, right? And it's encoded by a simple Gaussian process prior. If you're not familiar with that, then I'll highly recommend just reading a tutorial on Gaussian processes by Rasmussen. So it's a book available online for free, right? So you can just look through it. But this bit is encoding spatial smoothness, right? It's a statistical dependency. It's saying that I don't know anything about W. All I know is the locations at which these W's are being measured. And if I know these locations, then my first assumption is that it should be spatially smooth. That's it, right? That's the intuition. So the next, what you have all these wind informations that NOAA gives you, right? So there's no reason to throw that away, right? We should actually incorporate that in our statistical inference. So we say, all right, you know, these 176 locations across continental United States, let's consider them at least in our model, right? And what we know is that it's going to be a function of this wind field. It's not completely, you know, random, right? It is related to this guy, and that's what this edge is depicting. A relationship between, so the plate means that, you know, these random variables, well, the T's are the random variables that have been predicted by NOAA. They are repeated for NS 176 times, right? And there is a dependency, a direct dependency between what NOAA says and what actually the true winds are, right? Again, just all I'm doing here is just graphically depicting the statistical dependencies and nothing else, right? I mean, there's no algorithm right now. It's the mathematical model, right, of how things are in nature. And I'm going to say that, you know, the dependency is, I mean, the dependency is nothing but some Gaussian noise added to this wind, right? It's a noisy version of this guy. What NOAA is saying is a noisy version of it, right? And this is the noise model. Again, if you're not familiar with it, let's not worry about the exact form and function, but the intuition is just that this is the noisy version of your wind field, right? As I said, this is just explaining statistical dependencies, nothing else, right? And then you have all these aircraft information, right? You have 10,000 airplanes, right? And each of these 10,000 airplanes is, you know, experiencing some wind, right? The wind here is like not blue, it's white. Blue means that these guys are observed. So this is observed by NOAA, this is observed, these are locations. But this is not directly observed. Instead, what we observe is the ground velocities that the aircraft is going through, right? So this potential function here, right, is encoding the dependency, right, of the true wind, not the wind that the aircraft is observing given the ground speeds, right? So again, this is nothing but a statistical dependency model between different variables. W is what we care about, S is the set of locations. Tj's is the prediction that the NOAA is generating on its own, right? This corresponds to all the aircrafts, 10,000 or so. Here's the wind that the aircraft is experiencing, but we don't observe it directly, we only observe the ground velocities, right? And this potential function encodes the vector algebra that we talked about, right? Again, the form factor is not important right now, but I want you to appreciate the statistical dependencies. Yes?
So one question, just the rational when you say about the closed,
Yeah, so
or is it also geographical terrain of the
right now it's not, we are not encoding it. You know, the smoothness coming from this is only LLAs, which is latitude, longitude, and altitude. But you can consider a geographical feature as well in it. So it's over, say, a hilly region or over, you know, mountainous region. You can do that. Yeah, you can do that. So in that case, similarity of two locations will also consider that. But that's definitely one possible ways. But we are not doing it right now here. Yeah.
From the realization, the T's, how do you get the mean and the variance of the variable and variable?
Yeah, so that's the inference problem, right? I mean, we're going to talk about it. Right now, this is describing nothing. Let's see if I have the, well, I don't have the exact function, but we'll talk about it. What it's describing right now is the statistical dependency, right? That's it. I have not talked about any inference yet. This is saying that this is how all these things are related in nature, right? So if you have a test point, right, you're interested in, let's see, what's the probability that the T star takes a value, right? For instance, you might be interested in that, right? And so you can imagine that there's a black box algorithm where you say, hey, I am interested in wind at this location star, what is it? Given that you observe all these blue nodes. That's the inference procedure, right? I don't have the exact mathematical formulation for this guy, but here's what we can do. We can go back to our joint model. So a bunch of it back. Here, right? So here also now, you know, we can incorporate the same ideas for a joint model that considers the wind velocities, but also pressure, temperature, and the dew point. There what you do is, you know, again there's a GP prior as well, but then you have a neural network that is enforcing the joint dependencies of all the weather variables. So if I know my wind well, I kind of know a little bit more information about the pressure, and I can you know, push that information towards the pressure. Similarly, from the pressure you can go towards the dew point as well as to the temperature, and all of this thing is giantly coupled, right? So that's the neural network part. But what in the end, any of the graphical model like this encodes a probability distribution. So what's the joint probability of, you know, winds across given, you know, all the observations that you've seen, for instance, right? So a model results in a formula like this, right? All right, let's go. Too many clicks. Okay. Right. So now the next question is, how do the inference? How do I compute the posterior distribution over the entire wind field given what I have seen, right? So yeah, we'll get to this. I mean, I'll describe some of the experiments that we've got. The way to think about this is you know, machine learning using Bayesian inference as opposed to the traditional models of training and test data, right? So you know, in the first machine learning class that you might have taken, right? There is a whole paradigm that you train your models and then you test your models, right? But this is kind of, you know, thinking machine learning from the inference point of view. So for instance, consider a very simple classification task, right? You've some training data, binary classifier, right? And you want to make prediction on a test point. So what you will do is you'll have a training phase, you'll train your SVM or decision tree or neural network, and then you come up with a model and you apply that model on the test point, right? But in the Bayesian paradigm, you ask the question, what's the label at the test point given the training data that you've seen, right? So there is no training phase, you are just directly asking that question, right? And it's trying to, it has the notion of a model, but you're treating that model as a random variable and you're marginalizing over it. And it's the same idea here as well, right? So there's no training phase. You are subsuming all the training data during the inference time, right? And it has certain advantages because now you can carry through the uncertainty all the way through for your decision process. And we'll see in the future, why does that become interesting, right? Any other questions? Okay, so let's move on. So here is a field study we did, right? So what we did was the following.
Just a clarification.
Yeah.
In the previous slide,
Yeah.
so I guess beta, sigma,
Yeah, these are hyperparameters.
they have to be.
Yeah, they have to be tuned by hand, right? So for instance,
K is something.
so K is a kernel function. So K is basically your notion of similarity between 2 points.
It's a correlation matrix or.
So it's a correlation matrix, right? But instead of being any arbitrary correlation matrix, it's generated via radial basis functions. So take two ith and jth entry, look at their latitude, longitude, altitude, an RBF function on that, right? So it can be anything. It can be as long as it's semi-positive definite, you are fine. But the way we are generating is via RBF function. Right. All right. So here is an experiment that we did. It was a field study. In the it was a pretty interesting experiment. The experiment was the following. We took a weather balloon, right? And we tried to predict the trajectory of the weather balloon using different wind models, right? So it was released at some particular location. It went up till 100,000 feet. It had the GPS coordinates, so we can actually track what exactly the path that it took, right? So on the specific day, this was the NOAA was predicting, right? This is some other intermediate model, but this is what our model was predicting. So if you noticed, the NOAA model is kind of saying that the wind is mostly coming from the southwest, right? However, this model is saying that we are going a little bit more in the northerly direction, right? These triangles are again those locations where the NOAA makes predictions, for instance, right? So marked difference between what's coming out of NOAA and what's coming out of our model, right? So here is the result. So this was the trajectory. So this was the start location. This was the trajectory, the magenta line that was predicted if we use the NOAA model of the ground trajectory, right? It's a weather balloon, so it will just drift with the wind where the wind is going, right? So you can easily integrate your winds across time and come up with a trajectory. The blue was our prediction, and the black is the trajectory that the balloon took, right? So a real world, basically, confirmation of this technique is actually working fine. We are in the process of actually working with yeah.
I've got a question about the word prediction.
Mm-hmm.
So prediction typically means telling you something in advance.
Yep.
So when I think of weather prediction, I think about someone telling me what the weather's going to be like tomorrow.
Tomorrow, yeah.
But this seems to be,
No.
Noah seems to be doing prediction, but you seem to be doing real-time detection of what the
No,
wind
so this is
is that a fair comparison?
yeah. So what I'm describing here is the spatial part of the prediction, right? So you observe at say 5-10 different locations, how does spatially it will interpolate, right? But we have the time series aspect of it as well, because the reason is the following: if you exactly know at a very high granularity what's happening now, it will definitely help you make the predictions, right? So in fact, the follow-up work, which I'm not really dwelling upon, but I'm happy to discuss that as well. That is actually making future predictions as well, right? So in that case, your smoothness is not in space but also in time.
But is Noah not actually doing? Is Noah also meant to be doing real-time telling you what the wind's doing now as well as predictions?
Yeah. So they
comparing like with like.
Yes, exactly. They generate wind prediction models for current every 6 hours until I think 36 hours, right? So what the wind's doing now, what will they do 6 hours from now, then 12 hours from now, 18 hours from now, and every 6 hours they'll try to update using the satellite imagery, right? But this slide is like an hour long, right? So we just use the NOAA's current model to do that. But we have a follow-up work which is actually looking at the predictions all the way till 36 hours as well. right? But the whole intuition is the same. This is a very rich source of information. If you don't know what you're doing currently well, there's no hope of predicting in future, right? So this part of the talk is just telling you about what's happening now, spatially, but it does feed into your prediction model very, a lot. So, yeah. Yeah. Yeah, that's interesting. So these are the local phenomenons. So if you're familiar with the geography of the region, there's a huge cascade range that goes through, a huge mountain range. And there are very interesting effects on winds because of that. And since we don't have any geographical locations encoded in the model, it suffers from that, right? But yeah, this is we tried to guess what it was, but it's hard to. Right? We actually are also partnering with certain airlines who are actually feeding us the real wind data from their flight management systems, and we're directly comparing it. And looks like analysis like this is so very useful that they might use all these winds in the flight planning as opposed to the government winds. So, but yeah, is this a question? Yeah. You will do that, yeah. So you have to encode that in your smoothness matrix. Yeah, definitely. I mean, it was, definitely that's a possibility. The V1, we just went simple because, with encoding geographical terrain comes a lot of nuances, and we have to be a little bit careful about it. But you're right. I mean, in the end, it has to be a function of geographical terrain. Probability, yes. Yeah, definitely. All right, should we move on? Okay. All right, here is some of the error matrix that, the difference between end and all that. So this is actually a service is live. If you go on this URL, at least for continental United States, you will see, wind flow versus, the NOAA. This is the difference map, all the errors. So these are the interesting regions where the errors are. So if you go on the URL, it's running, every hour right now, right? I had Nitish Sood, I think he's not here, who actually worked on the Indian version of this service, right? And soon we'll be going live, because in India the weather balloons are even sparser. So it just makes sense to harness all this information, right? And so we'll be going live with that as well, just for the Indian subcontinent part, right? Here are some additional, numerical experiments, but in the interest of time, I don't think I've only gone through like probably 20% of my slides, so you can keep moving on. But the whole idea is that, so here's the time series prediction. We can actually take all that wind information and try to improve the prediction models. So this is wind prediction, but you are doing in future as well, not just current, but in 6 hours, 12 hours, and 24 hours. And how does the model improve on the error? So the green one is ours, lower the better. Right. And again, these are all in on the KDD paper that I can share, all the URL that you can take a look at in detail. All right, so we talked about sensing, right? An aircraft network is a giant swarm sensor network, right? What we also want to do is that now suppose you have to augment all this network with, say, quad rotors, a network of quad rotors. How would you determine what are the most important locations for us to deploy these quad rotors to, right? Any big organization probably have access to, a limited supply, right? You don't have infinite number of quad rotors. So how would you start thinking about deployment of these? Like, what are the most important places for you to deploy these airplanes? So that's the second part of the talk. So, information is is expensive. Right? Even the flight aware thing that I showed you, it might seem that it's all available on the web and it's free, but not really. I mean, you are using your bandwidth, you are using your computation power, there are time delays, right? In fact, flightaware.com, it charges query, it charges me 5 cents per airplane or something like that, right? It's pretty minimal, but still, it's if you add it up over a period of day, it turns out to be a few $100s, right? So if you have limited budget, then how would you decide on what are the right locations to ping so that you can get the maximum bang for the buck, right? And you might think about intuitively a quantity called the value of information. How many of you guys have heard the phrase value of information? Right? It's coming from decision theory, information theory, that aspect, right? But the whole idea is that if you can characterize some kind of a gain function, some kind of gain which is, so Q is the set of all the locations you are interested in making predictions about. Oh, sorry. So Q is the subset of all the locations at which you have deployed your sensors to. So for instance, I have only 100 quadrotors. So the 100 locations in space where I will deploy these things through, right? So that's the SQ. So gain is a function of where you deploy those quadrotors, right? And this gain is an information theoretic gain, and I'll explain that in a bit. But then there's also a cost related to these deployment. So if you look at this quantity, we are interested in finding a subset, SQ of subset of all the locations SA such that this quantity is maximized. So maximum buck for the cost, and this is a combinatorial optimization problem. So in general, if you don't know any structure for cost or the gain function, it's going to be NP hard, right? And 100, if that's your subset, if your set, the size of the subset, good luck, finding that out, right? So you'll have to resort to interesting optimization based techniques. So here is the notion of gain that's been very popular with Bayesian models, right? So this is the whole idea of information gain, right? Again, I'm not sure how many of you are familiar with the term entropy, right? So what we got, entropy characterizes the uncertainty in the system. So I showed you that Bayesian graphical model. It's a probability distribution. So consequently, what I can do is I can compute the entropy for that distribution. The entropy for my wind field given all the observed things, right? So that will characterize, the information content in the system. So the whole idea is the following. SL is suppose, the set of all the locations for which the NOAA gives predictions, right? So what you got is, you have some measure of uncertainty in all the sites, except the sites to which you will be deploying the sensors to, right? And so all you're doing is you're basically looking at what's the reduction, right? So this is the new entropy that you'll get when you add all the newly deployed sites to the labeled ones, right? So this quantity is just trying to characterize how much uncertainty shrinks in the system. And if this uncertainty shrinks quite a lot, that's good for you, right? So you really want to figure out a subset SQ such that this gain is maximized, right? Say that again? SI is all the set of all the sites you are interested in. So I for interest, right? So you might be interested in, for instance, wind predictions. It can be a subset of SA, right? But in general, it does not need to be. You can also say that I am only interested in, say, the southern tip of India for the timing for this prediction, right? But SA can be, the entire subcontinent, for instance, right? So it's a classic expression that people have used quite a bit. So any questions on this?
Does this mathematical expression boil down to telling that you will place the sensor at places where your model probably cannot give an exact?
So intuition, it's what it's doing is that it's reasoning about the sites. So if you go and place your sensors, it's going to shrink your uncertainty everywhere else maximally. So it's not just about those sites, but also about the sites of interest that you care about, right? So for instance, as I said, right, you might be just interested in, the southern tip of India to do some wind profiling. Why? Because, you care about some monsoon patterns or something, right? But that's the region that you care about. But given that, you have access to the entire Indian airspace, right? So the set of all possible locations SA is the entire country, right? But then you only have 100 sensors. So you can say, where should I put it? So these 100 sensors, since you're interested in the southern tip, most of them might be just deployed there, but some of them might get deployed near the Himalayas because, they have long range dependencies, for instance, right? So what it's just trying to reason is, how the information gain helps across the sites that you're interested in if you deploy at SQ, basically. That's the intuition.
And these sensors do come back, right?
Yeah, these sensors do come back. Yeah, yeah.
I mean, like, can't you resend them again and those things cannot happen, or it's
No, you can. It's cost prohibitive, right? It's cost prohibitive. Like every single deployment will cost in time as well as in money, right? So it's limited supply only. So you'll have to do reasoning irrespective, because the set of possible sites is almost infinite, right? So how do you solve this problem, right? If you are, here is an interesting, as a very important theorem that actually was proved like in 70s. How many of you guys are familiar with the phrase submodularity? So probably one or two of you, right? So the whole idea here is that submodular functions are a class of functions that exhibit the property of diminishing returns, right? So I'll give you a very simple example. Again, let's go back to the example of sensing temperature in this room, right? The majority of the information is going to actually come from the first sensor I deploy. It'll probably in the middle of the room, right? The second sensor that I deploy might not be in the middle of the room because there's already a sensor. It'll be somewhere, off-centered. It'll give you some information gain, but it's not going to give you that much information as much as the one that the first sensor gave you, right? So it's a diminishing return. So as you add more and more sensors, the information gain that you're getting, it's going to decrease, right? So the biggest gain is the first, the second biggest gain is the second one, the third biggest gain is the third one, and so forth, right? So it's the property of the diminishing returns. That's called submodular functions, right? And information gain, follows that nice property. So here is a very simple greedy algorithm that we are going to do, right? What you do is you select the sensors greedily one by one, right? So what you're going to do is you're going to start with an empty set, right? And then for all possible locations, like you have the list of possible locations from SA, you're just going to look at how much gain in the objective function that you get out of by adding this, right? And then you pick the location that gives you the biggest gain and you add it to the set, and you keep doing that, right? Just one. So instead of solving it combinatorially, you're solving it greedily. Just add one set location at a time. Very simple algorithms, but very profound properties, right? So one profound property of this thing is that if your function is submodular and monotonic, there exists no other approximation algorithm that's better than this. And that's a mind-blowing result. This is basically the only thing that you could do in approximation algorithm space.
What's the approximation factor?
It's 1 minus 1 by e, so 63% of the optimal, right? Well, there is a caveat. Basically, this is the best algorithms unless p equal to np. So it's coming. So if you guys are interested in it, right, I'll suggest read this paper, 2006, pretty path-breaking paper. Well, this is building on the results of the 1973 paper by Nemhauser and all, but that's the foundation. It describes all the intuitions and things like those, right?
So here, do you find your edge? You go back and look at matrix W and so on.
Yeah, compute the entropy. Yeah, it's order n cube. Yeah, it's order n cube, right? So there's lazy. So here is the interesting thing of this algorithm, right? The greedy itself is pretty expensive. Each step for this greedy is order n cube, where n is the number of sites that you might have. So even greedy you might not be able to do. So there are some interesting approximations to the greedy itself, right? So there's a whole line of research if any of you guys want to follow up on this, right? It's a pretty interesting area. But here is the more interesting bit that Dravyansh and Amit actually helped crack last summer. So this is the sensor selection problem, and the simulation, right? So here is the number of sensors as you place, and how your function, the gain in the function, right? So the greedy solution is the blue one, right? And the red is the optimal solution. So it's only 5 sensors, so you can do all combinatorial combination, right? So red is the upper bound. You can't ever do better than red, right? Red is the optimal. the blue, the greedy one, is very close to red. And the bound that comes out of the Nemhauser paper, this is around 63% of it, it's pretty loose. Actually, the greedy is within 0.98% of the optimal. And you see this phenomenon on and on, like why does this happen, right? And there is no good theory right now that can describe this phenomenon. Like, why is greedy so good? The greedy is almost as good as the optimal, right? So we try to develop some of this theory using curvature functions for some order functions. Again, this is I'm just mentioning it. There are papers online. You are welcome to read through it. But the whole idea is the following. This function, the red line, for instance, is a typical profile of a submodular function, right? So diminishing returns. The gain initially are very high, and then it flattens out as you add sensors, right? So if you go in this here as well, the gain is the highest here, and then decreases, and it'll flatten out, right? So that's the form of the submodular function. So what you can do is you can characterize, this shape, the curvature, right, using a curvature function. So what it is basically saying is that how fast your diminishing return is changing, right? That's what the intuition is, right? So for instance, for a linear function is also actually a submodular function, right? You can, the coefficient, the curvature coefficient is 0, but for submodular function, it's always greater than 0. I mean, there are some nice interesting properties with it. But the good thing is you can come up with a bound which is better than Nemhauser et al. Bound using this, these intuitions. Again, I'm just throwing these things out so that people who are interested in can follow up. This is our last year's ICML paper, right? And this work only focused on very particular kind of submodular functions that are generated by radial basis functions. The whole field is wide open. You can try different kernel function, different kind of submodularity, different kind of other tasks. So if you're interested in one interesting line of research, people who are theoretically inclined might want to think about. Right. All right. So last half an hour, let's try to see if we can cover this. So what you've done is you figure out a way to extract information, and then you figure out a way to how to deploy the sensors. The third thing is how would you carry out this mission safely, right? And again, this is a controls problem, right? So you have a quad rotor, right, or a device that can fly through space. So how do you make sure that it'll carry that mission, because he's going to, it's going to fly through uncertain environments. So let's make it very, very concrete. So here is a wind field. Let's say if I have this is the wind field, right? Say I have to go from point A to point B. In this wind field, the shortest path in time is never a straight line. It's going to be a contour, it's going to be a curve, right? So if I exactly know the wind field, I can compute the shortest path. So let me give you an example why this thing matters, right? A typical quad rotor, I mean, I know quad rotors are unfortunately banned in India, but have you guys, any of you guys flown a quad rotor, like a DJI? Okay, so those guys fly at 10 miles an hour, something like that, right? They can, the top speed is pretty high, but for 20-minute battery life, you're looking at 10 miles, 15 miles an hour speed. If the wind is blowing against you at 10 miles an hour, you're not going to get that much distance out. You need to start thinking about how to incorporate some of these uncertainties in your planning as a control mechanism in order to get the maximum boost, right? So consequently, you need to figure out shortest path in time. If you have a wind field like that, the shortest path in time is not a straight line, it's a curve, right? So if I exactly know this wind field, I know plenty of control algorithms that can give you the solution, right? I mean, it's a differential equation, set of differential equations. Throw it at MATLAB and it'll give you, I think MATLAB even have an example for something like that, right? However, the problem is that you don't know this wind field. You only have some idea, right? So as you're going through the wind field, you're reasoning about what's going to happen in future, and then you're taking your bets, right? I'm going to map it to an abstract problem, which is shortest path on uncertain graphs, right? So it's a graph You have a goal node and a start node. The only caveat that you don't really know the edge costs, right? So you want to solve shortest path, you know that these edges have some weights, but these edges are not revealed to you, right? So how do you solve shortest path on this graph? So the first thing we can do, in general, if you don't know anything about the edge cost structure, good luck. I mean, there's nothing you can do. This is an impossible problem to solve. But if you assume certain kind of constraints, right? For instance, in the wind case, there is some kind of spatial smoothness, right, that can be imposed, right? Then there is some hope of solving this, right? So specifically, you start from this node, right? You decide to take this edge. As you take this edge, the cost of this edge is revealed, right? So you know how much you incurred. But if you have some kind of a structure, cost structure, you can say, all right, if this edge is so and so cost, I have some idea of what the other costs might be, right? And so you can actually use that information. So as you're traversing through the graph, you are getting more information and you are making more informed choices. Yeah.
Probable distribution given an edge cost and then
Yeah. So it depends upon the on the problem domain. So for instance, in our wind case, we know that the edge costs are coming because of the wind structure, right? So you can assume a functional form of your cost, and then you have a distribution over a part of that function, right? And that's revealed as you go through. So for instance, right, if I see headwind of 10 knots here, right? So as you traverse this edge, you say, hey, the wind is coming from west 10 knots, right? So you can use that information saying that most likely in the nearby areas, I can assume the same thing, and then you can compute what the edge costs are going to be. And then you can have like a Gaussian process model that will percolate it further down the road.
it's going to be Gaussian.
In this case, right, but it can be anything. It can be Bernoulli. Actually, there's a generalization of this, not a generalization, a specific case of problem, which is called Canadian traveler problem, right? And the whole motivation is the following. It's a town in Canada where it snows quite a bit, right? So it's a grid, and you have to go from A to B, and with some, probability distribution, which is like Bernoulli distribution, there is snow on the road, so it's blocked, right? And you can assume that there is a smoothness. The roads that are in the neighborhood, they are more likely to be blocked together, right? As opposed to the roads that are at a different area, right? So that's the discrete version of it. But you can assume different kinds of distribution leading you to different, right? So the question is, how do you solve, shortest path in this thing? And yeah, you have a question? Yeah. So the way we did it is the following. So the question is that how do you translate that control problem, which is in the continuous space, to a discrete problem here? So what you can do is you can assume a grid, right? So think about a latitude, longitude, gridded. It's a discretized version of the space, right? And you allow transitions in either x, y, z or the 45-degree angles, right? So if at a node, as you are traversing the edge, you'll experience some wind, right? So based on that wind, you can project that wind on the neighboring edges as well, right? So that's how you're percolating it down, and the long range dependencies will based on your Gaussian process kernel. So GP, a Gaussian process, is going to percolate it down further, right? I mean, we don't really have much time to go in details, but there is a paper that describes the entire thing, right? But the whole intuition here is the following. I mean, what I want to describe in general is this shortest path on uncertain graphs problem, where your graphs might have some, there might be some cost structure associated with your costs, right? And the problem is how to solve this in general, right? Any further questions? Right. So again, as I said, the intuition is that the edge costs are not completely independent. There is structure to it, right? Because of the natural dynamics, spatial correlations, and things like those, right? So again, this is the Gaussian process model. Let's just skip through. Let's just look at some of the intuitions. So what we're going to do is we're going to solve this using hindsight optimization. So here is the intuition. I have some probability distribution on my edges, the cost of the edges, right? It's a joint distribution, right? When you take an edge, the edge cost is revealed for that particular edge, and then you can update the posterior distribution of all the other, unobserved edges given what you saw here, right? And then based on that, you're going to take your next action. So that's the model that you're going to do, right? The question is, what's the best policy to solve this? Right, so here's the best policy here is an upper bound on the policy, right? So here's what you're going to do. If I have a joint distribution over all my edge costs, I can generate samples, right? I can say, all right, from this Gaussian process or from this Bernoulli process, generate 1,000 different graphs, right? So every single graph is an instantiation from the distribution of the edges that have been given to me, right? So you have 1,000 different graphs. Solve shortest path on all these 1,000 different graphs, right? So that's what you're going to do. You have, here 6 graph only, but extended to 1,001. So you're computing the shortest path, right? Now what you have from each graph, you guys probably know what a Dijkstra's algorithm is, right? So dynamic programming. So you have the whole notion of the Q function, right? So basically it's measuring, for every action, what's the cost of taking that action and the cost to go from that action to all the way to the goal. So that's the Q function, right? So now for all these 1,000 graphs, I have Q functions for every action that are revealed to me for those 1,000 graphs. What I can do is I can just average them out, right? And that's my estimate, right, of what a Q function for the true problem is, right? I threw a lot of stuff at you, but any questions on this? I'll repeat myself. So what you're doing is you are sampling 1,000 different graphs, thousands or possibly, depending upon your bandwidth, 10,000 million. For each graph, you're going to solve a shortest path problem. And from each shortest path problem, you get the Q function, right? And now you have, 1,000 different Q functions. You just average them out. And that's going to be the approximate of the true problem that you're trying to solve. Yeah. So the reason that you're averaging is because you're trying to marginalize over the latent space, right? So the minimum will give you the best case, right? But what you want to do is you want to minimize your risk. And in order to minimize your risk, you'll have to consider all possible ways. So what might happen is that the minimum that you got is so unlikely that it give you minimum right now, but on an average, it's an unlikely event. So you want to integrate over all possible uncertainties. Right. Yeah. The parameters of the distribution. So you know that. So here's the thing. For instance, in the Gaussian case, you might know that this is a Gaussian distribution, but you don't know mean and the standard deviation. And when you take an edge, that's revealed to you. So that's one model, right? The other model is that the mean has been given, but not the standard deviation. And there's a third model where the standard deviation has been given, but not the mean. And the fourth model when you've been given mean and standard deviation. So all possibilities are subsumed in this thing.
But in a realistic scenario, you don't know those parameters also, and you're learning those as you're
Yeah. So you can make it as general as you want. You can make it very general where everything is pretty much a random variable, but then your computation costs go high, really up, right? Because now you have to do inference every time you get but this is in general, right? The algorithm operates, it doesn't make any assumptions about the distribution. It says, hey, if there is a distribution, this is a way that you can do it.
So
right?
your notion of the optimal path
Yeah.
now, because the path itself has a variation.
Yeah,
right?
yeah.
The path length
Yeah,
itself.
yeah.
So is it like you're looking at the mean of all possible paths, the path with the minimum mean, or what is it that you're?
Yeah, so the quantity that we're interested in is the time taken, for instance.
Correct.
Right?
That is a random variable.
That's the so and that's what you're optimizing over. So you're right. You might come up with different paths of different lengths, but what it's giving you is the following. This is only giving you a policy that this is a way for you to select the next action.
I didn't mean
right?
for this particular step. I'm just saying if you go back to the general problem statement.
Yeah.
You want to find the shortest path.
The shortest path,
But
exactly, in
every
time.
path has a distribution, right? So you're
Yeah. So let's. So in this case, right, I want to go from that corner to this corner. right? What's the shortest path in time?
That's right.
When this is known, I know exactly what it is. When it's not known, I'll have to do some exploration,
Right.
right? And that's what I'm trying to find. What should it be?
Now, what I'm asking is, any path you take,
Yeah.
there is going to be a distribution
Yes.
for that path.
Yes. Yes.
So it is quite possible that there is a certain probability that any path that
Mm-hmm.
could be the shortest one for that particular instance.
Yes. Yes.
So that's why I'm
Yeah. No.
asking the question, how are you posing the problem, the optimization problem? Is it you're looking at the min of the means?
Yeah.
What exactly are you?
So the way, the way the actual optimization problem is, argmin over all possible paths, right? Which is marginalized for the wind. So it's the average case. Does it make sense? So I'm not doing worst case analysis. It might be possible to do the minimax kind of things as well, but this is average case right now. Yeah.
We are talking about nodes and all here, right? In that picture, how relevant is that node? Because it's a random. I mean, depending on the distribution, you start taking one node, and that's how you assume.
So basically, think of this continuous variable. You put a grid of nodes there.
So this was a lot of them, right?
There are a lot of them. Yeah. So this is every 0.1 degrees we are plopping a node when we are implementing it. Yes.
And if we were to map this grid into the path thing,
Yeah.
we are also adding another complexity that the reward associated with each node is somewhat.
Not yet. I mean, this is not really submodular. Here.
Because as you're moving around, you are sampling the wind speed also, and you're interested in not just taking the shortest path.
Yeah.
Probably since you're anyway
Moving around.
the path
It's very good insight. So here's the deal. In this work, we didn't do this. There's a follow-up work that's coming out, which basically proves that, the scheme that we are doing here, because of that similarity probability, it's probably it's a no regret strategy. If you're familiar with the notion of regrets and bandits and online learning, basically saying that this is the kind of the best strategy you can do. It's a sublinear regret, but that's exploiting the similarity. And you're right. I mean, as I go through this thing, it gives me information, and the first step is going to give you the maximum information, right? And it's a good insight.
No, I'm just also saying that in addition to, so let's just move on from point A to B, right? Of course, there is a cost structure which has some modularity in it, and we
Yeah.
have to exploit it.
Yeah.
But since you're anyway moving around, you also want to sample the wind speed, because
Yes.
that is the eventual.
Exactly. Yeah.
And the reward associated with each point that you sample the wind speed at is also submodular.
Submodular. Yeah.
So now there's a cost function
The-
which is loss in process. There's also a reward.
Reward function is submodular as well. Yes. In fact, yeah.
You want to probably maximize the reward by minimizing the cost.
Cost. Both are submodular. Yeah. In fact, yeah. In fact, I mean, if you see the, some of the paths that you generate, they do exploration initially, and then they quickly figure out what to do, right? And this is because of some modularity property, both in the cost as well as in the reward structure. Right? All right, so I think you guys got the intuition, right? It's a pretty straightforward, and again, some more experiments and things like those. I'll just refer to the paper instead of going through this. So here are a few of the papers that are describing our work, right? The first, if you're interested in the smaller part of it, this is the ICML paper. That's just looking at the entropy case, and then talking about the curvature functions and etc. Right? The wind data, the wind experiment is the airplanes Aloft as sensor network paper that was presented a couple of years ago, and there's a follow-up work that actually extends the winds to the future time series as well as to other variables of interest. And the shortest path problems is it's the AMAS paper in 2014. So we still have 10 minutes. So at this point I think it's a good idea to sort of I'm happy to answer questions. Happy to talk about some other future work that we've been looking into. I mean, up to you guys. Yeah.
Yeah, so you use the quadrotor to get a sense of the wind and the other temperature parameter. So how did that model work compared to the aircraft model which you used?
So So for the, I mean, those experiments we are actually running this summer, but I can give you a peek of some of these things. The biggest problem with quadrotors right now is that they will not go very high because of regulations. Right now they are 400 feet, right? So locally you'll get extreme good measurements, right? So for instance, so Ranveer spoke to you guys, right? He probably talked to you about the agriculture, the IoT aspect of it. So the local wind models are very important in the context of farming. The reason being that, for instance, the pollination of the crop depends upon the wind patterns, right? You can actually have a quadrotor go through and create detailed wind profiles using techniques similar to that, right? So in that context, we have done, some experiments, and those are pretty encouraging, right? But in the context of weather, we can only go up to 400 feet right now with the quadrotor. So we are in the process of getting approval to actually deploy at the high altitude. But hence, the airplanes, Aloft is a proxy for that, right? So if you could do that, then it will give you a sense of, how much reduction in error there is. So if you go through the paper, it will give you exact quantities. So for instance, I'll give you some basic numbers. If we just use the aircraft Aloft framework and no quadrotors, right? The error using, the airline that we are working with, the errors in the direction of the wind is reduced by like 30% or so, like 30 degrees or so. And that's a lot of error in the wind direction, right? And in terms of wind magnitude, I mean, again, up to like 10 knots or something. So pretty significant improvement in those terms. But that's not using quadrotor, that's just using the aircraft Aloft. So. Hurricanes, the wind models are extremely, highly refined, right? So you can do a path prediction of storms very accurately using those. That's something we haven't really done any experiments on yet, but it's one of the big motivations of this work, right? So, but yeah, if you want to follow up, we can work on that. Yeah.
Do you see something like, you can stick on some sensors to planes and all, is that possible?
So AMDAR, they already thought about it, right? So they have, it's a gigantic exercise in organizational, basically you have to get all these airlines on board.
Actually, I'm asking this because can you also track ocean currents in a similar fashion?
Yes, you can do that. Yeah, you can do that, and I mean, there's the same public data that's available for aircraft is also available for oceans. Similar techniques could be applied. We haven't done it, but if there is interest, I'm sure we can actually share the code and things like those. But very similar principles. Right? All right. So I think if there are no questions, I can just briefly talk about last 5 minutes. A couple of future research projects that we've been looking into. Right. Again, feel free to chat with me if you'd be interested in working on some of these problems. So the first problem is, let's just look at in the context of the controls. Right. So this problem, right. So this the notion of submodularity in the cost and the reward structure, right. So the problem of finding shortest path in uncertain graph in general is NP hard, right. You can come up with a policy, but the open question is that the policy that you're going to run in this context. So if you guys are familiar with Markov decision processes, you can map this into Markov decision process and come up with a policy, and then you want to make statements about the regret of that policy, right. We have some interesting, I guess, intuitions that tell us that it will be a sublinear regret, but then the open question is, how well can you do? Can you actually come up with square root t kind of regret bounds, for instance, right? So that's one thing that we'd like to think about. In the same space of things, right, you can come up with a generalization of a Markov decision process, which is not just shortest path in time, but optimizing a function that has a latent variable, right? And that latent variable is coming from some physical process. And then again, thinking about, the questions of regrets, exploration, and exploitation in that space. So that's some of the things that we are actively working on in our group. In terms of, the wind flow. Oh well, even beyond this. So this whole notion of curvature, we applied it to a very specific form of information gain, but it'll be great to extend that to other submodel functions in general. So how could we do that? That's again an active area of research, and Amit Deshpande at Microsoft Research India is actively working on it as well. So that's another open problem if you guys are interested in working on. And finally, we also want to talk about the whole aircraft aloft in the air, right? We want to extend this to the worldwide, the wind models, right? And while we've been doing to India, but I think there is a big need for the global wind model as well, because if we can do that, then long range flights might be very very efficient, both in terms of carbon footprint, but also in terms of fuel consumption. But right now it's only for continent US and India. But and if any of you guys are interested in pursuing any of these lines, just let me know. I think I'm sure we can chat about it in detail. Right? All right. So finish 2 minutes early.
In some part of this graph is highly populated and some part is not that sparse kind of thing. So when you are considering that you are predicting some kind of global thing.
Yeah.
So how you can manage the sparse, especially I can say that over the oceans, the aircraft especially follow a particular path or particular route. So
you
how can you manage that sparsity here? That's
I think it's a good question and possibly a research direction. So what you're asking is that, look at these areas, right? Some of them are sparse, some of them extremely crowded, like, New York, all the East Coast, right? So how to deal with sparsity? One idea is you can actually ask airliners to route their airplane, right? Depending upon your value of information. In fact, you might be able to come up with, this is like going in the realms of operations research, where you might be able to come up with pricing models, where someone like NOAA or the government pays airliners extra money or gives them subsidy if they would consider routing the airplane through those. And that can be a dynamic process. Or more importantly, if an airline has a fleet of airplanes, in order to maximize their, their fuel efficiency, they might decide to sort of have some of these aircraft do a little bit of a longer path, maybe a few minutes, but it might give you that valuable information so that the costs are optimized across the entire fleet, right? So those are some of the things that you could do. Right? Again, the sparsity only affects your final cost function. If your cost function is just wind in this area, you don't really care. But if it's say, there's a hurricane over there, you might want to sort of consider ways of getting more information. But that's again, combining control with perception and doing value of information analysis. But yeah, another research project, I think.
No more questions?
I think just
yeah.
observation actually that your shortest path, I'm sure there are a lot of other applications also.
Yeah.
I kind of see that for
and
example, in VLSI design we have this
issue
of finding longest paths. Because they determine the speed of a chip. And essentially one needs to do and the paths have this kinds of randomness.
Yeah,
right?
I think
so in
that's
that
great.
process, how do we?
It'll be good to sort of chat about this. I didn't know about this application. I know people in networks, computer networks, who are looking at switching packets. I mean, they're also thinking about along the similar lines. There's the stochastics in terms of congestion, in terms of traffic, and this is it's a great application. It'll be great to learn about it more.